Hello students, welcome back to the 11th physics class after half yearly exam. Okay, so now we start a new chapter, work, energy and power. So we also studied little bit about idea we have about the work, energy and power, because we also studied in class 8, 7, 8 this classes, okay, and 9 also. So let's talk about first work. So work means we know that whenever we apply a force on an object, and if that object will be displaced from its position, that means it will displace a certain distance in the direction of the applied force, then we said that is called work, or we can say that work has to be done by that object. Okay, so we know this one, that work done means, or we know that the main conditions for work done is, one is the applied force, another one is the point of application of the force moves in the direction of the force. That means two things is needed, very important for work done. One, a external force exerted on a body, and body will displace from its position in the direction of the applied force. These two are the main condition for work done. If these two things are happened, then we can say that the body or an object has to be done, work has to be done by that object. Okay, and for work done there are many examples. Here I will write only two. Many examples of work done. Work done means if the body is displaced by the applying when the applied force is applied, then we say that will be work done. So many examples are there. So two examples I will write here, that is horse pulls a cart, an engine pulls a train, a bus. Okay, or whenever you pull an object or box, and when you displace that table or chair from its position by applying an external force, that is work done. If there is no displacement of an object, but you applied the force, but still there will be no displacement of the object, then we can say that there will be no work done. There will be no work done, or it can be said as zero work done. So zero work done means the displacement is zero. You apply a force, for example, let the wall. Okay, whenever you apply a force on the wall, you apply the external force, but the wall does not displace from its position because it is a very heavier object than your applied force. So it will not displace. So that time we can say that the work done is zero work done, or no work has to be done by that human being, or by you or by me. Okay, so that is called zero work done. Clear? Now this is a simple way we define the work done. Now if a constant force applied on an object, then how can we define, and with a certain angle, then how can we define the work done? In this figure you see that an object will displace a certain distance s by applying a constant force F, and this F will makes one angle theta. Theta is the angle which F makes with the positive x direction of the displacement. With the displacement, that applied force makes an angle theta. So now in this case, how we can determine the work done? So as we know that force is a vector quantity, so we take a component of force along the displacement vector, and because it is a base component, so it always cos theta, F cos theta. So in this case we consider the force component, that is F cos theta, which is acted along the displacement. It's represent the force which is applied on an object. Clear? So in this case, in place of F, we write F cos theta, because here F constant force makes one angle theta. To determine the work done, we consider or we resolve the force vector in two components, but the another one components no need. So we take the base component, that is F cos theta. So work done, how can we write the work done? Work done, as we know, that force multiplied by displacement. So here work done equals to force means F cos theta multiplied by displacement, that is S. So Fs cos theta. Okay, now in vector chapter we studied that when we have cos theta, when the dot product between the two vectors, then in place of a dot product we write the cos theta, and after dot product, whatever the product we get, that is always a scalar quantity. When the scalar quantity we get after product after multiply two vectors, that is called dot product. So here in vector form we can also write W equals to F dot S, but W, the work done, is a scalar quantity. W is a scalar quantity. F and S both are the vector quantity, because here the cos theta is present or the dot product is present, and we know that from dot product we get whatever the quantity we get as a product, that is scalar quantity. So work done is a scalar quantity, and its value either it will be positive, negative, or 0. 0 already we give the example, and later also we studied when we say that the positive work done, when we say that negative work done, and when we say that 0 work done. Okay, so in vector form we can write W equals to F dot S. Otherwise in normally magnitude form, W equals to Fs cos theta. Now here also we apply two cases. If theta equals to 0 degree, theta equals to 0 degree means the displacement and the force will be in the same direction, okay. So if it will be same direction, then theta equals to 0 degree, so W equals to, we get F into S, because cos 0 value is 1, so W equals to Fs. Now if we consider here the displacement is perpendicular to the applied force, that's why we did not draw here the perpendicular component, because our vector quantity, when you resolve the vector quantity, it will resolve in two components, one is a cos theta, another one is a sin theta. So here I will not draw the sin theta because of this second reason, that means sin theta, okay. That because theta, if theta equals to 90 degree, then W equals to, or you can say that if F cos theta is acted like this way, it can be perpendicular to the displacement vector, so work done also be 0. W equals to 0. W equals to Fs cos 90 degree, cos 90 value is 0, so W equals to 0. Later you also understand when we say that cos 90, theta equals to 90 degree, when. For one example, in a circular motion, we have theta equals to 90 degree in each, and because radius from the center, each and every point, it will be same and it will be perpendicular to that object, so that angle will be 90 degree. So in a circular motion, you move in a circular motion, that means the no work has to be done by that object or the body. Clear? Okay, so the two cases are there, theta equals to 0 and theta equals to 90 degree. So if theta equals to 0 degree, we get W equals to Fs, maximum work done. Theta equals to 90 degree, no work done, 0 work done. Now, because we studied already vector form, the chapter rectangular component, so this work done also be represented in terms of rectangular component, because work done equals to F dot S. F is a force vector, S is a displacement vector. So each and every vector has a rectangular component, so work done can also be represented by its rectangular component. So how we can represent? So F is a vector. If we consider the three axes x, y, and z, and the unit vectors along x, y, and z are I hat, j hat, and k hat. So F vector can be written as Fx I hat plus Fz k hat plus Fy j hat plus Fz k hat. Similarly, S equals to Sx I hat plus Sy j hat plus Sz k hat. we can write the rectangular components of force vector as well as the displacement vector. Now we know that the formula W equals to F dot S. So F, put the values here. So we know that in a dot product I dot I equals to 1, but I dot J, the dot product between two different base vector will be 0, and the dot product between same two base vector, that will be 1. So I dot I equals to 1 and I dot J equals to 0. So W equals to, we can write Fx Sx plus Fy Sy plus Fz Sz. This is the rectangular form of rectangular component of work done. W equals to Fx Sx plus Fy Sy plus Fz Sz. Clear? Okay. Now we talks about the dimensions and units of work done. So dimension means if you don't remember this one, you can also find out from the formula. Work done equals to force into distance or displacement, you can know. So force dimension is ml to the power minus 2, and the distance or displacement, that is a length, so multiplied by L. So the dimension of work done is ml square t to the power minus 2. This is the work done dimensions of work done. And the unit of work done, there are two types of units of work done. One is absolute unit, which unit we all normally we can use this in absolute unit. Another one is a gravitational unit. Okay, so first two absolute units are there. One is a joule, it is a SI unit, absolute unit of work on SI. SI absolute unit of work done, that will be joule. So work done is said to be 1 joule when a force of 1 Newton actually moves a body through a distance of 1 meter, because in SI we know that the unit of force is Newton and the displacement is in meter. So whenever the 1 Newton force is applied on a body, and if the body or the object displaced by 1 meter, then only we can say that the work done is 1 joule. So 1 joule equals to 1 Newton into meter. Okay, and in Cgs system, the absolute unit of work done is arc. You know this one, I know, because you studied this 2 units in lower classes. So the Cgs system, the absolute unit of work done is arc. And similarly, how can we define arc? In Cgs system, the force will be dyne and the distance in centimeter. So we can say that if one dyne force is applied on an object and the body moves a distance of 1 centimeter, then we can say that work done is to be 1 arc. Okay, so 1 arc equals to 1 dyne into centimeter. And there will be one relation also be there, one arc and the joule. So that is your homework. Okay, in a comment box you write what is the relation between joule and arc. Clear? Okay, now next, gravitational unit. These are the practical units. Practical for when we find out the work done, then that time we can use this unit, or otherwise normally we use the absolute unit. Mainly we use the joule. So that's because it is a SI unit, that's why. So first gravitational unit in SI, that is kilogram meter. Gravitational unit of work done on SI is kilogram meter. So kilogram meter, how we can define? Kilogram meter means the force is kgf moved by a body through a distance of 1 meter. 1 kg force of kgf force when we apply on a body, and if the body will move 1 meter in the direction of the applied force, then we can say that work done is said to be 1 kg meter. Okay, 1 kg meter equals to 9.8 joule. Okay, next is a gram centimeter. Gram centimeter, so the force unit is g gram force and the distance will be 1 centimeter. Then the work done is said to be 1 gram centimeter. This is a gravitational unit of work done on Cgs system, and 1 gram meter equals to 980 arc. and the 1 kg meter equals to 9.8 joule. Next, nature of work done. Already we and I told that positive, negative, the work done are three types. Either positive, it will be positive, or negative, or zero. So as we know that the work done is a scalar quantity and its value may be positive, negative, or even zero. So positive work done means for best example, for positive example is a free fall. When a body falls freely under the action of the gravity, that means the body will displace in the same direction and the force also applied on the same direction. Theta equals to 0 degree, and theta equals to 0 means cos 0 equals to 1. So work done by the gravity for freely falling body, W equals to Fs, that is positive work done. So for positive work done, theta must be less than 90 degree. Must be less than 90 degree. Theta is an acute angle. So if theta equals to less than 90 degree, then the cos theta be positive. Hence the work done is positive. Or we can say that in a language, in a sentence, as we apply the external force and the object will displace in the same direction of the applied force, that is theta equals to 0 degree. Already we say that for that example, that time we can say that this is a positive work done. That means the applied force and the displacement of the object will be in the same direction. That is called positive work done. Negative work done, just opposite. When we apply a force in a certain direction but the object will move in an opposite direction. For best example, when you throw a body, the gravitational force acts downward direction, but the object, because you throw it, so it will displace in an opposite direction of the gravity. That time the work done by that object, that is negative. That means in this case the theta is greater than 90 degree. If theta is greater than 90 degree, then cos theta will be negative, because in this case when you throw a body in an upward direction, theta equals to 180 degree and cos 180 value is -1, so W equals to minus of Fs, that will be negative work done. So you remember, if the displacement is in the same direction of the applied force, then it will be positive, and if the displacement is opposite direction of the applied force, then it will be negative. For positive, the theta is always less than the 90 degree and it is acute angle, and for negative, theta is always greater than 90 degree, it is obtuse angle for negative and positive work done. Another work done, 0, already we discussed. 0 means when theta equals to 90 degree. When the applied force or the displacement vector is both at the 0, or we can say that both are perpendicular to each other, then the work done is 0. Then the work done is 0. For best example, another one example, when you move in a straight path with hold one suitcase in your hand, that suitcase will displace in a straight line, but the gravity acts on that object, it will be in a perpendicular direction. So the force and the displacement vector, force and the displacement are perpendicular to each other, so there will be no work done, 0 work done. So force and displacement, if perpendicular to each other, then we can say that the work done is 0 work done, because cos 90 degree value is 0. Another one, when we push a hard wall, that already I discussed, so S equals to 0. If displacement is not there but the force is present, okay, then also be the work done is 0, because in this case the this also be the perpendicular, because wall does not move and you apply a force perpendicular on the wall, so theta equals to 90 degree. So in this case also work done is 0. Okay, so positive work done, negative work done, and zero work done. Another one example in a circular motion. In a circular path, if you move, then no work has to be done by you. Okay, now we see two numericals related to this work done. So here in the first numerical, here you see that the force expression sum 2 I hat minus 6 j hat Newton is applied on a body. It is given, and the body will displace minus 3 j hat. So here the it will be minus 3 j hat meter. How much work is done by the force? So if value is given, s value is given, we know that the formula w equals to f dot s. We put the value over there because I dot j is 0. So the work done will be 18 joule. 18 joule minus plus 3 into 6, 18 joule. J dot j1. Clear? So the work has to be done by the force will be 80 joule. Next one, a particle is acted upon by a constant forces F1 and F2. Expressions are given. These are the two constant forces. Constantly it will apply on an object. So first of all, we find out the resultant. Resultant F equals to F1 plus F2. We put the value, so we get the expression of F. I hat minus J hat plus K hat. And the object will displace from a point A, coordinate is 2 comma 1 comma 0, to the point B equals to minus 3 comma minus 4 comma 2. So B is a final. So the how much it will be displaced, the displacement vector expression B minus A. So I x, y and z, that means minus 3 I hat minus 4 j hat plus 2 k hat minus of because final minus initial, then we get the displacement vector 2 I hat plus j hat plus 0 k hat. So we get minus 5 I hat minus 5 j hat plus 2 k hat. This is the displacement vector. So we already get the expression of force vector and the displacement vector also. Now you put these two values in the expression or in the formula w equals to f dot s. Now if we put it over there, you get 2, because no unit is given, so only we can write 2 units. If unit is given Newton or meter, then only we can write the joule, but no units are given. When this type of numericals are there, then only you can write unit. So whatever the unit is SI, it will be joule. If it will be Cgs, then it will be R. Okay, so the total work done by these forces is 2 units. Clear? Okay, so I think no problem arises because you know these things. These numericals are new topic, and these expressions for rectangular expressions, these things are new. But other things you know, the idea about the work, energy and power, already you know this one. Just little bit new, few things are new in this chapter. Work energy theorem, the variable forces. If this is a constant force applied on an object. If the variable force applied on an object, then we use the integration. Okay, this topic, these things are new in this chapter. Otherwise, the concept will be same. So thank you very much. If you have any problem, any confusion, please type in a comment box. Thank you. Have a nice day.